Thank you for coming to my talk today, titled Continual Audit of Individual Fairness in Deployed Classifiers via Prediction. And this is joint work with Ivoline Ngong and Joe Nair, who's my advisor in computer science. So for today's talk, I'm going to spend some time talking about some of the challenges of fairness in algorithmic systems, our auditing mechanism called prediction sensitivity, smooth prediction sensitivity, and our current work. And I will also spend some time talking about how we define and quantify fairness and unfairness in our work, as well as some of the challenges and limitations in our work. And finally, I will talk about the direction of our future work. So one of the challenges of artificial intelligence and big data has been in the area of making fair evaluations. So on the bottom left, this is an article from Vice magazine from 2020, in which an ex-driver filed a lawsuit accusing Uber of violating the Civil Rights Act by firing minority drivers based on its rating system. So Uber used its star rating system at the time to terminate drivers, which purely from a metric evaluation seems reasonable, but resulting in disparate impacts on non-white drivers. So the article talks about Thomas Liu, who noticed that in San Diego, riders canceled ride requests after he had accepted once they were able to view his picture, with some riders asking where he was from. The article also talks about the possible dangers of other businesses attempting to replicate Uber's model that uses a semi-autonomous system to collect user ratings and evaluate whether to hire or fire human drivers. The top right is a Wired magazine article from 2020, in which Tom Simonite writes about how in New Jersey, when a judge has to make a decision on whether to hold someone until trial or release them, they have to take into account this algorithm called Public Safety Assessment, or PSA, that estimates how likely you are to skip court or commit another crime. So it's making an assessment that predicts failure to appear in court pretrial, new criminal arrest while on pretrial release, and new violent criminal arrest while on pretrial release. And so the article mentions that in an open letter in July 2019, academics suggested pretrial risk assessments be abandoned because the tools are built on data and reflect racial and ethnic disparities in policing, charging, and judicial decisions. And one of the things the open letter referenced in the article said is that the actuarial pretrial risk assessments suffer from serious technical flaws that undermine their accuracy, validity, and effectiveness, and that they do not accurately measure the risks that are required by law to consider, since they rely on these deeply flawed data, such as historical records of arrests, charges, convictions, and sentences. And they state in the letter that for the same conduct, research has shown that African-American and Latino or Latina people are more likely to be arrested, prosecuted, convicted, and sentenced to harsher punishment than their white counterparts. So these complaints have been echoed in this pivotal case on the top left, in which Robert Julian Borchak Williams received a call from the Detroit Police Department telling him to come to the station for his arrest. So he was handcuffed on his front lawn and only shown a piece of paper with his photo and the words felon, warrant, and larceny. And his wife, when asked where he was being taken, was told to Google it. And his mugshots, fingerprints, and DNA were taken, and he was held overnight and interrogated. As it turns out, this case is the first known account of an American being wrongfully arrested based on the flawed match from a facial recognition algorithm. And this is after federal and academic studies had found that facial recognition systems misidentified people of color more often than white people, showing Asian and African-American people were up to 100 times more likely to be misidentified than white men, depending on the algorithm and type of search used. And so one of the issues, as an example, is that the faces of African-American women were being identified falsely more often in searches used for police investigations, where an image is compared with other images, hoping for a match in identifying a suspect. So we as a society are constantly trying to balance the need for automation and technology with these humanistic issues. And I read an article a few days ago by Drew Harwell, who has done extensive journalism research in this area, in which the IRS most recently had abandoned its plan to require millions of Americans to submit a face scanning service offered by a company called ID.me for authentication. And this is because the IRS immediately received criticism from privacy advocates and members of Congress, not just for privacy concerns, but also for the issue that it would unfairly burden Americans without smartphones or computer cameras, and that it would subject people of color to a system known to work less accurately on darker skin. And the same system also was found to more likely misidentify women than men, and the elderly and children more so than those in other age groups. The system also showed the highest accuracy rates for middle-aged white men. Researchers Joy Balamwini, Timnit Gabru, and Deborah Raji have done extensive work on algorithmic bias in their groundbreaking research, Gender Shades. Since then, the White House Office of Science and Technology Policy has been developing principles to guard against technologies while gaining input from the public. And this is an important problem because many of these automated tools or data sets are being used to do things like learn features of a company's employees to reject applicants who are dissimilar from existing staff. And this is problematic because it might exclude perfectly qualified applicants like female computer programmers or lead to rejection from a mortgage based on one zip code, as features might be extracted, such as zip codes, that might be correlated with race and poverty, amplifying bias over time. With this in mind, our world is becoming more and more technology dependent. And this can lead to, for those persons living in poverty, oppressive surveillance technologies that exclude marginalized communities in an effort to sanitize the presence of unwanted communities from smart, high-tech cities. So what is the balance of designing and implementing technologies that allow human beings to live with dignity? So it's tricky because even within the companies that make these technologies, there can be bias internally. So there have been countless studies showing that particularly within technology companies, there isn't much diversity. And we see this as pervasive, especially at the leadership level at these companies. And in 2021, a survey of 2030 workers between the ages of 18 and 28 was conducted by the Wiley Report. 68% of respondents said that they have felt uncomfortable working in a tech role because of their gender, ethnicity, socioeconomic background, or neurodevelopmental condition. And even at an early age, male respondents of the survey were found to be more likely to say that they were encouraged into tech careers by their high schools and colleges. Additionally, for those of you who have worked or do work at tech companies, there is an inherent thinking that they can be the change in the systems that they want to create. But with homogeneity of the industry, how can they arguably create the best solutions? As we saw, there are high stakes implications for justice and fairness if the products that are being built in the technology sector aren't considering or representing users. So on a positive note, I wanted to highlight MacArthur Fellowship 2021 recipient Josh Meal as an example of a person who was able to bring his perspective to create a broader conversation in the technology space. He works as a principal accessibility researcher, coming also from a deep background in psychoacoustics, and he has spent his life developing tools to make the world accessible for people who are visually impaired. And some of the work he has done includes being on the group of designers and developers who built the Echo family of devices, Kindle, Fire tablets, Fire TV, and Amazon Basics microwaves. So you should definitely take the time to read the entire article, which is in Amazon Science. But the part of the article that resonated with me was that he said that usability testing is a fairly well-known art. But when you're testing with specialized populations, like people who are blind or deaf, or people using wheelchairs, there are certain adjustments that you want to make to your research protocol so that you're doing things the right way. And having someone like Josh, who doesn't emphasize technology for technology's sake, optimization, but rather doing things the right way might make all the difference within these companies building products for people. So during the course of this research, some of the questions we were considering in this space were things like, who determines if a system is fair? Systems can inherently inherit a hierarchical societal structure that might determine fairness by majority rules, or might just turn out to be really unfair for specific individuals. So in these cases, who is allowed to be critical of these systems? And how does one seek recourse? Another question we might think about is, or that we did think about, was whether our evaluation might be based on a dominating group or have group fairness where the average is considered versus individual fairness, or even fairness on a subgroup level. And how then would we determine these subgroups as are informed by collected data, which may or may not have inherent biases depending on who collected the data. And finally, as someone who isn't originally from the United States, and one of the other first authors, Ivy, is also not from the United States. She's from Cameroon. We thought about what the broader effects of these systems might be. So many countries inherit legacy systems. For example, in emerging economies, systems like these might be directly transferred from first world countries or even tested on persons in the developing world. So what are the ramifications of these choices with respect to fairness and bias? And so one of the papers we looked at was a paper by Zachary Lipton et al., which was titled, Does Mitigating ML's Impact Disparity Require Treatment Disparity, from 2019. The paper talks about how existing legal doctrine has qualitative ideas about mitigating machine learning discrimination, but machine learning systems require concrete formalism, and it produces results on several real-world datasets to highlight the practical consequences of applying two notions of disparity, which they identify as treatment disparity and impact disparity. They call the reconciliation of those methods disparate learning processes, or DLP, and use the principle that the protected characteristic may be used during training, but it is not available to the model at prediction time. So they generate synthetic data to corrupt the data with a synthetic discrimination to create an unfair world, which simulates historical bias in the training data. And they use experiments on real data to show that when DLP disrupts the within group ordering and violates the do no harm principle by disadvantaging a non-advantaged group that, if it weren't for DLP, would have received favorable or equitable results. And one of the most important points from this paper is that group fairness is not often enough to tell the full story, and that sometimes mitigations might make predictions better, but for some individuals within groups, they might experience a worse outcome. So one of the issues is that within the definition of fairness, the definition can be difficult to determine because we don't know which definition to use based on a task to be performed. So how do we formalize fairness quantitatively? And can this be done? And what are the trade-offs and limitations of our method? So one of the questions that we asked in our paper was whether the model would have made the same prediction if the protected status had been different. So the paper Counterfactual Fairness by Kusner, Loftus, Russell, and Silva defines counterfactual fairness as being an intuition that a decision is fair towards an individual if it is the same in the actual world and the counterfactual world where the individual belonged to a different demographic group. The paper demonstrates their framework in a real-world problem of fair predictions in success in law school and includes several definitions of fairness, such as fairness through awareness, or FTU, which is where an algorithm is fair as long as any protected attributes are not explicitly used in a decision-making process. Individual fairness, which is IF, where an algorithm is fair if it gives similar predictions to similar individuals, and demographic parity, DP, where the proportion of each segment of a protected class should receive the positive outcome at equal rates, and equality of opportunity, or EO, where individuals who qualify for a desirable outcome should have an equal chance of being correctly classified for this outcome. And counterfactual fairness allows a clear correspondence to informal fairness, but it is a challenge and hard to measure in practice. And this is specifically because it requires knowledge of causal information. So that is, how does protected status cause other features to be the way they are? And we almost never have this information or knowledge in practice. So counterfactual fairness is really difficult to measure directly in any practical setting. So we created prediction sensitivity, which asks how the model would rely on the protected status when making a prediction. Prediction sensitivity captures the extent to which predictions depend on the protected status of the individual. It doesn't attempt to improve predictions, but rather raises an alarm for bad ones. It draws on differential privacy by drawing on the concept of function sensitivity using differential privacy. And by looking at a weight and computing for a feature vector X, the partial derivative of the prediction with respect to one feature, we ask, how much does a model rely on the protected attribute, which indicates membership in one group or another, by taking the prediction itself and looking at its gradient. And in prediction, the gradient determines how the model weights should be moved to remove the loss. We're asking the question how the prediction would change if the person were not a member of the group they're currently a member of. So if we move them from an advantage to a non-advantage group, how much has that prediction changed? And we do this by looking at the gradient of the prediction itself with respect to the protected attributes that indicate membership in one group or another. So as we said, prediction sensitivity is based on gradients of predictions made by two models. The protected status model A is trained to predict the protected status of an individual from their features. The classifier F is a model we would like to evaluate. The protected status feature weights is a gradient of the predicted status, and it measures how each feature influences the individual's protected status. So the per feature influence is the gradient of F's prediction, and it measures how each feature was used in making the prediction we would like to evaluate. The dot product of these two is a prediction sensitivity. The dot product effectively weights each feature's influence on the prediction by its influence on the protected status. So we approximate counterfactual fairness with this measure. For example, whether the model relied on protected status is likely to be correlated with counterfactual fairness because reliance on the protected status implies that a change in protected status would have changed the prediction. So conversely, if the model did not rely on protected status at all when making the prediction, then it definitely would have made the same prediction if the individual's protected status had been different. And as we said before, within the fairness research community, there are often controversial definitions of fairness. So what does an unfair evaluation quantitatively look like? Can unfairness be quantified with a computer? Some of the questions involving fairness in the fairness research community have been things like, can fairness be quantified with randomness? And other questions are machine learning itself, and whether it's been successful in algorithmic bias systems, whether it should be used at all, and if so, to what extent. And if it is not used fully, should there be human intervention? And should this human intervention involve specific domain knowledge, for example, in fields like AI and health? Another question has also been that for automated algorithmic systems, whether persons should be warned if systems are being used for evaluation, and whether by knowing that such systems are being used, participants would attempt to interpret and game the system for favorable result. So one of our research questions was whether prediction sensitivity did in fact measure counterfactual fairness. So our progress involves evaluating prediction sensitivity based on generating synthetic data using a causal model. So we determined a ground truth for counterfactual fairness and measured this against prediction sensitivity. So using synthetic data here allows us to know the causal information that is usually missing in the real world, so we can get a valid ground truth. So we use scikit-learn to generate synthetic data sets consistent with the causal models or graphs that we could use to show biased synthetic data in which a causal relationship exists between the protected status and outcome. We trained the classifier F using data consistent in the model and the counterfactual fair classifier and computed prediction sensitivities and constructed a distinguisher, which we call D, to determine the threshold theta that allows trading off between false negatives and false positives. We then constructed the receiver operating characteristic curve, so ROC, and calculated the area under the curve, or AUC values, for this distinguisher by varying theta, performing 30 trials of the experiment. So our approach was to train two classifiers and then compare their prediction to detect failures of counterfactual fairness. So the original classifier is F, which may or may not satisfy counterfactual fairness. And the second model, the unbiased classifier F hat, is trained on modified data to ensure counterfactual fairness. So we show a causal graph for biased synthetic data in which a causal relationship exists between a protected status and its outcome. And we show a modified causal graph that removes this relationship. We determined that data generated according to the second model can be used to train classifiers that satisfy counterfactual fairness. And we use this evaluation to find individuals for whom F and F hat make different predictions, which we call enumerating matched sets in the paper. So the reasoning is that since F hat is determined to satisfy counterfactual fairness, a mismatch likely indicates a failure of counterfactual fairness for F. So we call the set of individuals for whom both models make the same predictions a matched set. And what we found was that the average prediction sensitivity is much higher for counterfactually unfair predictions, and that prediction sensitivity can be used as a classifier to detect unfair predictions with high accuracy. So the left graph shows the distribution of sensitivities, and the right graph shows how accurate a classifier based on prediction sensitivity is for detecting unfair predictions. And our evaluations were done using the adult dataset and the COMPAS dataset. We used predicted attributes, sex and race for the adult dataset and sex and race for the COMPAS dataset. We compared the average area under the curve, or AUC, for the original and the counterfactually augmented datasets. We're able to plot these results using a logarithmic scale on the left-hand side. And what we saw is that for all cases, the average prediction sensitivity is much higher for non-members of the match set than it is for members. So some of, in the paper, we talk about counterfactual augmentation used in our experiments. And so the goal of using counterfactual augmentation is to approximate data drawn from a similar distribution to the original data, but without the causal relationship between protected status and outcome. So our approach modifies only the protected attributes and leaves the other features alone. And some of the challenges and results we found were that the results that we found suggest that prediction sensitivity is effective in measuring counterfactual fairness. However, they seem to show that the average area under the curve, that AUC, is significantly lower than the AUC for our synthetic data experiments. And what this means is that there could be two factors that account for this. One factor could be that bias is less severe in real data sets, so failure of counterfactual fairness is harder to detect. And the second factor could be that our approach to counterfactual augmentation could be missing significant correlations between other features and protected status. So what this suggests more largely is that prediction sensitivity is effective at detecting unfair predictions, so that individual predictions with extremely high prediction sensitivity are likely to be blatantly unfair and can be easily detected, but those borderline cases are more difficult to detect. So in our future work, we hope to address borderline cases using prediction sensitivity, as well as look at other methods for evaluating the effectiveness of prediction sensitivity. So at this time, I'd like to thank you so much for taking the time to listen to this talk. If you'd like to get in touch with myself or my collaborators, feel free to do so. And you can find our recently published work. We just posted it on arXiv. And I'd also like to mention that this work was funded by an Amazon Research Award. So thank you so much for your time.
Thank you so much, Crystal. Thank you. That was a really interesting talk. I'd like to open the floor up to questions. I think you should be able to unmute, but you could also use the hand raise function as well for questions. I can start. Oh, go ahead.
Gonna ask, hi, Crystal. This is really, really interesting stuff. I have a ton of notes on everything you're referencing here. I was curious, is this something that would work on any type of model? Are there like black box models and things? Is it kind of a generic approach to thinking about fairness?
So we are, throughout the entire research that we've done so far, we've really been trying to be careful about the assumptions that we've been making. And from the beginning, I think we're very clear about the fact that we're not going to say that this makes things fair, because that's within the fairness space that's been very controversial. But people saying that, oh, we've mitigated a model and made it fair now. What does that mean? But we hope, and right now we're doing testing in general to see the extent to which the mechanism does seem to indicate that something is fair and or unfair. So we do hope that it can be used more generally, but specifically, it started because there was a lot more work in the AI research community that focused on group fairness. And it's like, well, I mean, we're not all the average of the group. So for some individuals, when you have high stakes, you don't want to have an average be acceptable. And so we veered in the direction of individual fairness, which tends to be, it makes more sense. I think Cynthia Dwork has a Simons Foundation talk that she just released on fairness and randomness that I was watching last night. And one of the things she says is that individual fairness makes a lot of sense because it's very task-based. So it's harder to generalize. So I think that there are trade-offs, but we hope that we can get some good results from more generalized studies. Thank you.
Thanks. Yeah, I know the fairness definitions are always kind of tricky, like saying anything is fair. Definitely come across that trying to parse it out in the literature. So thanks for clarifying that. Any other questions for Crystal? I had a question about the synthetic data, and if you could go a little bit more into how you created that, or the process of determining how that was going to happen. I'm really interested to hear about that.
So that particular issue has also come up in the fairness community where, so those two data sets, the adult and the COMPAS data sets, are known to be kind of problematic data sets. So I think you can only get up to like 73% in the adult data set if you train it and say, oh, I want this much accuracy. But there's still this issue of what does fair and unfair look like quantitatively? And one of the solutions that people in the fairness field have kind of tried to think about which is in that Zachary Lipton paper, is they have sort of a flip test where they generate a fair and an unfair world, and kind of you manipulate it in a way that's deliberately unfair, that you'd say, oh, this should not happen at all. And you compare whether in our case, prediction sensitivity will detect that there's some degree of unfairness baked into that particular model or that particular data set. So there's three papers. That Zachary Lipton paper is the first one that has, I believe it's like gender and length of hair. So they talk about simulating that the data set, the unfair worlds, which is kind of used as a baseline, because within fairness, that baseline of what unfair looks like has been really problematic. Like if you go into the fairness space and you say, can you give me a data set that's unfair? Then there's not a data set that really exists like that. There are any things that you can measure that might be proxies for things that might result in an unfair prediction. So when you're testing to see whether something would be fair or unfair quantitatively, one of the solutions has been to generate that synthetic data set where you deliberately make things unfair and measure to see the extent to which it's predicted to be an unfair decision. And then there's also a second paper, it might be by Kristen Lum and others, called Flip Test. And those two papers kind of talk about different ways of thinking about how to evaluate on things like synthetic data sets, fairness and unfairness quantitatively.
Got it. Thank you so much. It's really interesting to think about how you would construct a data set like that to test, like it's almost like a stress test kind of for fairness mechanism to have that kind of data set. So that's really interesting.
Oh, I like that. I should use that in the next talk. Stress tests. Great, thank you. I'll credit you too.
Thank you so much, Crystal. Are there any other questions from our participants? Just want to make sure we. Okay, thank you so much again, Crystal.
Thank you. Have a nice day, everyone. Okay, bye.
Thank you. You too. So I would.